Good morning, everyone. I'd like to thank the organizers and the CREA for inviting me to come back to this lovely place that I've visited several times before, but it's actually been now a couple of years since I've been here, and I'm very happy to be back. So I'll be telling you about cosmic reionization and the redshifted 21 centimeter signal. And this is actually not, so I'll explain why the epoch of reionization is an interesting epoch to study and why it was important in understanding the history of the universe. And I'll briefly give an overview of how we can find out what happened during that period, and then specifically what we can do with the radio telescope, new radio telescope LOFAR that I'm involved in, and also look at, to the future of when the square kilometer array will contribute to this. Now, the times I visited Morelia, though, I didn't work on reionization here. I worked on the dynamics of H2 regions, so the growth of H2 regions in turbulent molecular clouds with Will Henney, Jane Arthur, and Enrique Vasquez. And here's a movie showing a growing H2 region in such a turbulent medium. And so this is photoionization coupled to magnetohydrodynamics. And you get nice pillars and globules and temperature fluctuations and lots of lovely things. Now, the research I'm talking about is also photoionization, but on much larger scales, on cosmological scales. So, the history of the universe, part 2, which is the observable part, starts with the cosmic microwave background. So there was a history before that, but that's unobservable and can only be calculated. So we can observe the cosmic microwave background, which comes to us in a largely homogeneous way. And if you zoom in on the fluctuations, which is the picture you see here, there are small fluctuations of order 10 to the minus 5, which are the density fluctuations at that time. And the material that we see here is neutral. And so this is some 300,000 years after the 300,000 years after Big Bang. Then, if we look around us, we don't see a universe that looks like this. We see a universe filled with galaxies and clusters of galaxies, and the density fluctuations are much larger than this. They've grown over time, and you also find that most of the universe is actually nowadays ionized. Most of the baryonic matter in the universe is ionized. And so the question is, how did we get from this neutral, small fluctuation universe in the beginning to this high fluctuation, largely ionized universe that we see around us now? And in this story, the epoch of reionization is really the watershed period, because you could say that at the beginning of the epoch of reionization, the universe was much more like we see in the cosmic microwave background, a neutral universe with some density fluctuations, bigger, which has grown over time because of gravity, but still rather minor. And then at the end, we have a completely ionized universe with fairly developed galaxies and even small groups of galaxies. And so it starts roughly, we think, at redshift 50 and is more or less over by redshift 6. And this is a period of 700 million years, which at that time is roughly a Hubble time. So it is a time scale on which large cosmological evolution can occur, but at the same time it's driven by stars, and this is only 100 generations of massive stars. So in terms of stellar evolution, this is actually a fairly short period in which the universe was changed completely, because we started with a neutral universe with only hydrogen and helium left over from the Big Bang nucleosynthesis, and largest collapse objects were maybe dark matter halos of about 10 to the 5 solar masses. And at the end of this period, we have a largely ionized universe. There's metals and dust around. It looks much more like the universe we see around us today. And the largest collapse objects are actually bigger than the Milky Way dark matter halo. So this is what we call the epoch of reionization. Now, another interesting aspect of this is that when we look around us now, most of the baryons are actually missing, or at least we haven't observed them, because most of the baryons in the universe sit in between the galaxies in the intergalactic medium. it's ionized, it's low density, and they don't really produce any observable radiation or at levels that we can observe, then the picture that we get from the CMB is essentially all of the baryons in the universe at that time. So we can see all of the matter in the universe at that time. And the epoch of reionization is in that sense also a watershed period, because this is, we think, the last period where we could actually make a map of all the baryonic, or most of the baryonic matter in the universe. And this is shown here as a map of redshifted 21 centimeter signal at some redshift, and there's some ionized regions and still lots of neutral material. So this is the last period where we could actually take a picture of how the matter was distributed in the universe. And the picture of the cosmic microwave background has been compared to the baby picture, or has been called the baby picture of the universe. And if this is an adult universe, you could say that the epoch of reionization actually is a set of images, as we'll see, from the childhood of the universe, and so filling in this gap. So it's also an epoch of firsts. So the first stars form during this period, the first galaxies form, you form the first supermassive black holes. This is the time when the globular clusters formed, and in general, the building blocks of the Milky Way that are galaxy. And as we heard in Anatoly's Klipin's talk, this is also the period in which the smallest galaxies were suppressed, were evaporated by ionizing radiation and don't occur anymore. So how can we find out more about the epoch of reionization? And here sort of comes back these two pictures. So we have the picture of a galaxy survey, so the universe we see around us today, where you can see the individual galaxies, calculate the correlation functions, etc. And there's the CMB, where you see sort of the distribution of matter in the medium. And so the epoch of reionization, because it's this watershed period, you can on the one hand, if you come from the low redshift side, you can try to find the galaxies that are forming. And this has been very successful. There have been several successful programs, mostly with the Hubble Space Telescope, to find galaxies at very high redshift, going into the epoch of reionization up to redshift of 10. But the other approach would be to try to find the intergalactic medium. And this is, again, this picture, which is still from a simulation, so we don't have any data yet. But this is the other way we can study this period. So either finding the galaxies or finding the intergalactic medium. So how do you find the galaxies? There are different techniques for this. The most productive technique has been deep broadband photometry, mostly with the Hubble Space Telescope, where you look for so-called Lyman break galaxies. And this is, if you go into the epoch of reionization, this is the gray box here is supposed to represent the spectral energy distribution of a typical galaxy at that time, and it stops at this wavelength because this is the wavelength of Lyman alpha redshifted to that redshift of the galaxy, and blueward of Lyman alpha, no emission comes out because there's too much neutral medium between us and the galaxy, and all the Lyman alpha photons are scattered out of the line of sight. And then if you observe these galaxies with different broadband filters, you basically don't see it in V, V, I, Y, etc. And then at some point it starts showing up. And therefore you start looking for objects that show up in the reddest filters, and that then gives you high redshift galaxies, and it also gives you a handle on the redshift. So with the HST, of course, this has been done with these ultra deep fields, where you go very, very deep and get very faint objects. If you instead go very broad, like with the Sloan Digital Sky Survey and the VISTA telescope at ESO, you actually cover a large area, and so you only pick up the brightest objects from that epoch, and these are the quasars. So that's another way to find objects from that period, to actually go shallow, but very wide area. And then the third way is to look for Lyman alpha emission from galaxies, and this you do with narrowband surveys. And this has been most successfully done with the Subaru telescope. So just to illustrate again this dropout technique, so here's a picture. This is a Redshift 10 galaxy, which you don't see in the optical and in these filters, and then it starts showing up here and in the Spitzer. Well, I don't know if it really shows up here. So these objects are always called candidates, because until you take a spectrum, you can't be 100% sure that it is a very high redshift object. Now the future for this will be the JWST, which will, I guess, continue with these kind of surveys, the ELT, or I guess I'm taking European perspective, the European ELT, and the Euclid mission. So if you instead want to look at the intergalactic medium, there is currently only one way to do that, and that is to take a spectrum of a high redshift galaxy and see how the radiation blueward of the Lyman alpha transition is being suppressed. And this teaches you something about how much neutral hydrogen there is in the intergalactic medium at that time. And so you can do this with quasars, with Lyman alpha emitting galaxies, or with gamma ray bursts. But this gives you only an observation along one line of sight, and it's quite difficult to interpret because Lyman alpha is a resonant transition, and so you only need a neutral fraction of 10 to the minus 3 or 10 to the minus 2, which is quite highly ionized, to completely suppress all of the radiation blueward of Lyman alpha. So, but this is the only thing we currently have. But we hope within a couple of years to actually have 21 centimeter emission or absorption against a cosmic microwave background with LOFAR or the WA or PAPR, and then in the further future SKA. Or if we can find a high redshift radio galaxy, you can try to do 21 centimeter absorption against a bright radio galaxy, which should be easier to do, except we don't know any bright radio galaxies at high redshift yet. Now there's another way to probe the intergalactic medium, and these are indirect measurements, where you actually find a measure of the integrated electron density between us and, in this case, and the cosmic microwave background. So the electrons scatter cosmic microwave background photons, and this introduces a polarization signal, which has been measured by WMAP, and that's shown here. And so on large scales, there's this excess polarization, and this is due to the amount of electrons between us and the cosmic microwave background. And so it's sensitive to when first large amounts of electrons occurred in the universe, in other words, for when reionization happened. And this is normally expressed in an optical depth for electron scattering, tau. And this suggests that reionization happened, most of the action was around the redshift of 10 or so. But it's an integrated measurement, so it doesn't actually give us any details on how gradual the process was, for example. In addition, you can look at another effect on cosmic microwave background photons, namely the fact that the electrons are moving around and scatter the photons, and this introduces the kinetic Sunyaev-Sildowich effect, which has people trying to measure with the South Pole Telescope and the Atacama Cosmology Telescope. And there's some first results of this, which also put constraints on reionization. So these are existing observations. If you combine all the existing observations, you can try to derive how reionization happened here, expressed as the mean neutral fraction in the universe as a function of redshift. So it starts completely neutral, and it's mostly ionized by redshift 6 or so. And these two figures are from different papers which claim to use all the existing observational constraints there are. And the take-home message here is that they actually don't find the same result. In other words, the current observations don't really constrain how reionization happened. And in this paper, they actually give the 2 sigma variation on this, and you can see that there's, basically we know it's neutral at very high redshift, and we know it's ionized below redshift 6, and in between it's largely, well, could be anything almost. So this is the current problem. We don't actually know how this process developed over time. And this is where the 21 centimeter redshifted 21 centimeter observations will be coming in, and we'll try and we'll pin down how exactly reionization happened. And we've been working on this for several years, and I'm very happy that as of December last year, we're actually doing or November actually, we had an early start. The official cycle 0 of LOFAR was started in December. We're actually collecting now data to try to detect and subsequently characterize the 21 centimeter signal between redshift 6 to about redshift 11.5. And this is called the Epoch of Reionization Key Science Project with LOFAR. One of the 5 key science projects with LOFAR. So what is LOFAR? So LOFAR is a new generation radio telescope, an interferometer, where the elements of the interferometer are actually not dishes, like with the VLA or Westerbork or the GMRT in India, but they're actually antennas, dipole antennas, where the signal from the different antennas is combined electronically to make a so-called phased array. So you point your telescope by introducing electronic delays between the different elements in your station, in your groups of antennas. And here you see a picture of the core area of LOFAR in the Netherlands, and you see the 2 types of antennas that are in LOFAR, the so-called LBAs, the low band antennas that measure between 10 and 70 megahertz. So these poles with wires. Part of the wire is actually active, so this is the first 1/3 of this is the actual antenna. And there's hundreds, there's 96 of them in one station, and there's about 24 stations in the core area. Then the other elements are these high band antennas. They're also dipoles, but they're hidden in these big plastic boxes, and they observe between 110 and 250 megahertz. So we're not observing between 70 and 110 megahertz, and this is because of the FM radio band. Now for reionization, these are the antennas that we're using, because these ones could in principle give an interesting result about the early phases, but we don't have the sensitivity to actually get to this. Now it's always good to realize that there are different perspectives on things, and so we see another entity here, and so I thought it would be interesting to show the perspective of this Buzzard on LOFAR. So he also likes LOFAR a lot, because there are lots of interesting poles which are observing platforms to look for small mice or rats to hunt for, and he loves floating over these dark plastic boxes which produce lots of thermal lift. It's actually interesting, the LOFAR core area is a nature reserve area now, and so it actually combines science with nature conservation. So here's an overview of the entire LOFAR. So this is a map of northwestern Europe, and you see the different international stations. Here, one in Sweden, and this is an aerial photograph of the station in Sweden. So again, you see the LBAs here and the HBAs there, and the little container with all the electronics. So stations like this are in the UK, in France, and 5 of them in Germany. Then if you go to this area in the northwest of the Netherlands, there are lots of antenna groups there, and with a big concentration in this area here, which is called the LOFAR core, which looks like this, which actually has a core of a core, which has a very dense configurations of antennas. The large circles here are the LBAs, and the small circles are groups of HBAs. So all of the signals from all the antennas are actually sent to a supercomputer in the city of Groningen to be correlated and further processed. So we have from the commissioning phase already some results, and things look really quite promising, although we're exploring a regime of radio observations that hasn't really been explored before very much. So here's one of the fields that we'll be observing for the Epoch of Reionization experiment, because it has fairly weak galactic emission. And you can see here the difference between observing the same field with the old Westerbork telescope, equipped with low-frequency front ends, and with LOFAR. So within about, well, actually less time, you achieve a noise level which is 10 times better. And in general, you see that the data is much better calibrated. Most of these things are actually due to bright sources such as Cassiopeia A and Taurus A. And these have been effectively removed here, but for the Westerbork data, this turned out to be much more difficult to do. So LOFAR is giving superior results on this already. Of course, just a field of some, okay, maybe I should point out, the little dots you see here are all radio galaxies. So they're radio galaxies all over the sky, and they have to be removed from this, and we have to go deeper, much deeper, about a factor 100, about a factor 10 deeper, so 100 times more observing time to actually start to see be able to see the Epoch of Reionization signal. So, of course, LOFAR can also look at other objects. So this is the A-team, as it's called. These are the brightest radio galaxies in the northern sky. Brightest radio objects in the northern sky. They're not all radio galaxies. Cas A, a supernova remnant. Taurus A, also known as the Crab Nebula, also supernova remnant. And then these two radio galaxies, Cygnus A and Virgo A. And these are all images made by LOFAR of these objects. So what do we want to observe? How do we want to observe the Epoch of Reionization with LOFAR? So I already hinted at this. This is the classical 21 centimeter transition of neutral hydrogen, the forbidden hyperfine transition between the two ground state levels of hydrogen, where the parallel spins between the proton and the electron and the anti-parallel. The energy difference corresponds to a frequency of 1.442 gigahertz and a wavelength of 21 centimeter. Now, if you observe this from the high redshift universe, you can write down this expression for the measurable quantity, which is the differential brightness temperature. And this is actually, you measure the 21 centimeter transition against the background of cosmic microwave background photons. And so this differential brightness temperature can be actually positive when it's in emission or negative when it's in absorption against the cosmic microwave background. So this expression shows that the signal is sensitive to how neutral the hydrogen is. So this is the neutral fraction of hydrogen. The density of hydrogen, here expressed in delta, the overdensities of delta is 0, then it's the mean density of the universe at that redshift. Redshift, of course, and then this quantity, which is the spin temperature, basically the excitation temperature of the neutral hydrogen, can compare to the CMB temperature. And so you see if the spin temperature is very much higher than the CMB temperature, this term is positive, and you have emission. And it actually, this whole term goes to 1, so there's a ceiling to how bright the emission line can be. If so the spin temperature is less than the CMB temperature, this term becomes negative, and it can become very negative, so that actually in absorption, the amplitude of the signal is higher. Now for the range of redshift that LOFAR will be observing, we expect this term to be positive, and we'll see the emission we see the signal in emission. And then of course it depends on various cosmological parameters, the baryon density, the matter density in the universe, primordial helium abundance, and the line of sight velocity gradient. And I'll come back to this term later. Now, I said that basically observing the 21 centimeter emission is like making a map of the sky from that at redshifts, let's say between 6 and 12. So this actually means that it's better than the CMB because we get not one map, we get lots of maps at different times. So it's a whole sequence of maps. And this is expressed in, I guess, in the radio, what radio astronomers like to call the image cube. So you actually do an observation over a bandwidth nu of frequency, and you get different images at different frequencies. And these images, because the frequency that you observe at is essentially the redshifted 21 centimeters, so it comes from different cosmological redshifts. So you get basically a picture of the universe at different times. And this is shown here. This is a cut through this image cube from a simulation that we did, and it corresponds to this cut. So this is the frequency axis, which is also the time axis. So this is early, and this is late, and this is one of the two spatial axes. And so you see that as you move from, in this case, from about 130 megahertz to 190 megahertz, you start out with a signal where there's lots of small H2 regions, and as more and more galaxies form, you form bigger and bigger H2 regions, which remove most of the signal, and by the end, by 190 megahertz, there's almost no signal left. So we'll get basically maps at different frequencies. So this means that these image cubes actually, they come with spatial information, temporal information, and also velocity information. Because if the gas has a peculiar velocity, it will actually shift away from the cosmological redshift, either a little bit bluer or a little bit redder. So this means that if you do this observation, you actually get, if you fly through this image cube, you fly through space and through time. So what you see here is a little movie made from the simulation, where this is the redshift, so this corresponds to cosmological time, this is the frequency, and you see the fluctuations. This is smoothed to about 3 arc minutes resolution, which is typical for what LOFAR or even SKA could achieve. And you see the fluctuations changing, partly because you're probing different parts of space, and also because there's a gradual evolution in the amount of neutral hydrogen. So this image is also, we've subtracted the average signal, which is what an interferometer does. So this is what we get in an ideal world. So as you can see, this is quite, in a way, quite complicated data, and so we need to develop new ways to analyze this. And if you get this kind of three-dimensional data, it's called tomography to analyze this. And people have been working on developing tomographic methods. So, for example, trying to characterize the typical size of ionized bubbles at different times, or trying to measure doing topological measurements, for example, the Euler characteristic, which is a variation on the genus. And this is work of a PhD student of mine, Martina Friedrich, who looked at the evolution of this genus for different ionized fractions. So here's everything's neutral, and here it's completely ionized. And what you see is a typical evolution where initially this quantity increases, and then it decreases, and then it increases again. And initially, this is because what you have is so-called meatball topology, which means you have isolated H2 regions. And that gives a very, the more regions you form, the higher this Euler characteristic becomes. But then as this develops, it becomes much more like a sponge, where the different regions start touching and forming tunnels. And that actually reduces the genus of the distribution, and that's why you get this large negative slope. And then towards the end, you only have a few neutral regions left, which is again more similar to the meatball topology. So can we actually do this with LOFAR? Well, the problem is that if you do the calculation, you find you have a signal to noise of about 0.2 per resolution element. So no, we cannot do imaging with LOFAR. However, there may be limited ways in which we can actually image fairly large structures. So if you go to the end of reionization, and you smooth your data to, so this is at 3 arc-minute, but if you then smooth to about 20 arc-minutes, there's a chance you may pick up some large neutral patches. And this is supposed to show, it actually shows how difficult it is, but there is some correlation between this input signal and the reconstructed signal. If you're a little bit earlier and there's large ionized regions, large meaning something like 20, 30 megaparsec, you may be able to pick those up by searching your raw visibilities with a matched filter, which is something that I worked on with a postdoc Kanandata. So that's shown here. We did this simulation where we put in a bright quasar here in the middle of the box, and this is what you have if there were only stars, and this is the quasar has made this region a little bit bigger. And then we turned this into so-called visibilities, which is what the raw data that an interferometer produces, and then we searched with a spherical filter through it, and we find that basically you pick up the location of this region. So it is for reasonable assumptions about how much noise the telescope generates. So it should be possible to pick up some of the larger H2 regions even with low-fi. So no imaging, well, limited imaging. So what are we going to do? Well, we're going to look at statistical measurements of the 21 centimeter signal. This is both partly because we have to do that, and partly, of course, also is you can look at these images, but to some extent they look just like noise. It's the statistics of the images that should teach us about the physics of what's going on. Now, luckily, the 21 centimeter signal is very rich in properties, and I've listed a bunch of them here in different ways that we may be looking at it. I'll look at this. I'll talk more about this one and the last one. So the global signal. Now, if you take a single dish telescope and you point it to the sky, you measure this, then you get basically what is known as the global signal. So this is the brightness in millikelvin of the signal for 4 different simulations. But there's a general trend that the brightness goes down. And this is just expresses the fact that more and more of the universe becomes ionized. But to measure this, you need a single dish telescope, and it's going to be quite challenging because the changes of the signal with frequency are rather smooth. Now, if you take an interferometer like LOFAR, you cannot measure this. So for all the radio astronomers in the audience, this should be obvious. But so the problem with an interferometer is that you don't have so-called zero baselines, which means when you measure the sky, you essentially are insensitive to the average signal of the sky. You only see the fluctuations. And so the global signal from the point of view of an interferometer are the fluctuations in the signal. And if you calculate how the fluctuations evolve, you get a very different picture. So you start out when the universe is mostly neutral at some level, then it dips because the highest density regions tend to get ionized the first because that's where the galaxies are. But then as you form big H2 regions, the level of fluctuations goes up again. And then as the signal disappears, it goes down. And so this typical dipping and then reaching a maximum and then going down is seen in essentially all simulations. So this is what we hope to observe with LOFAR. And this is then the mean level of fluctuations, which should be measurable with a reasonable signal to noise. You can plot this in terms of the mean ionized fraction. So here the universe is completely neutral, here it's completely ionized. And then you see that this initial dip corresponds to something like 20% ionized, and this maximum here corresponds to about 70% ionized. Depending on the details of the model, this could be also 50, so it's sort of 50 to 70 is where this big peak is, and this can also shift around a little bit. But measuring these two things should allow us to pin down the reionization history of the universe quite well. Now the next step is to actually look at how the power is distributed over different scales, and that's what is done with power spectra. So here are a couple of examples of power spectra, again from simulations for a progression of, so this is 80% neutral, 50% neutral, and 30% neutral. And what you see is that initially the power spectrum looks very much like the matter power spectrum, and then as you start developing these bigger ionized regions, you get excess power, and you get a clear feature from the typical scales of the H2 regions. On the larger scale, it's just a scaling that goes with the mean neutral fraction of the universe and the bias of the sources. And again, this typical behavior is seen in many different kinds of simulations, and so this will help us also pin down basically the size distribution of H2 regions, which should teach us something about the sources, what galaxies contributed most to reionization. Now the 21 centimeter signal though has other properties, and one interesting property that I've been working on recently together with students and postdocs are the redshift space distortion. So when you observe the redshifted 21 centimeter signal, most of the redshift is due to the expansion of the universe, a cosmological redshift. So you redshifted from 1.4 gigahertz to, let's say, 140 megahertz for redshift 9. But if the gas has a certain velocity with respect to you, it will be slightly blue or redshifted away from its cosmological redshift. And the thing is that this shift away from the cosmological redshift is not random, but it depends on essentially it's driven by the matter distribution in the universe, because high density regions will generate large velocities as matter falls into high density regions. And if you make a map, so this is what it looks like. This is the neutral density distribution in the simulation, and this is what the signal would be if you introduce the redshift space distortion. And you see all these ripples forming, which are due to the fact that the signal tends to concentrate in the higher density regions and tends to be moved away from the lower density regions. And so this is well known from galaxy surveys, and there it's known as the Kaiser effect, because of course galaxies follow the same thing. But here you get it on a whole field, which is kind of interesting. And the thing is that this contains information about the density field and how the density field connects to the ionization field. And you can actually, what we studied was whether this fairly subtle effect is still measurable with LOFAR, and it turns out that it is. So the red dots here, this is for two different scales. The red dots here show a measurement of the strength of this signal, and this is the blue points are when we leave out the signal, so you can see that it's measurable. And it also, we plot the three lines are different reionization models, so it actually shows that you can distinguish between different reionization models. So this is quite interesting aspect of the 21 centimeter signal to explore. Okay, a little bit about the future. So plans are underway to build the largest radio telescope ever, the Square Kilometer Array. The Square Kilometer Array will have different sets of antennas located either in South Africa or in Australia. But one of the sets of antennas will be low frequencies antennas that are roughly going to be sensitive from frequencies 50 to 250 or 300 megahertz. This is an artist's impression of what it may look like. I think it's still rather early days. So SK low, as it's called, is the low frequency part of SK. It will be located in Western Australia, which is a much better site than the Netherlands, especially for the frequency range 70 to 110 megahertz. The collecting area will be close to a square kilometer, hence the name, and we hope that at least phase one, which will not reach this, but a fair fraction of this will be ready in 2020. So what will SKA contribute that LOFAR can't do? Well, the first thing is that it will actually allow us to make images of this type. So 3 arc-minute imaging of the 21 centimeter sky at different frequencies. And then we'll see where the holes caused by photoionization from the galaxies are. And we'll see some of the density fluctuations in the neutral regions. Additionally, SKA will allow us to go to higher redshift, where this term is not necessarily positive, but can be negative, when the spin temperature is smaller than the CMB temperature, or at least in some regions will be smaller. It's thought that by the time reionization gets underway, so let's say around redshift 12, most of the intergalactic medium will have been heated by early Xray sources, because you don't need many of those to actually raise the temperature of the intergalactic medium to above the CMB temperature. But if you start measuring around redshift of 15, say, all these numbers are highly uncertain because they're just based on models, but you may be able to see cold and warm regions, and therefore you can map how this heating by early Xray sources actually worked and how it depended on how its spatial distribution was. And then if you go even earlier, redshift 20, you'll see essentially the effect of UV radiation from the earlier stars on this signal. Because the spin temperature only couples to the kinetic temperature of the gas if there's enough Lyman alpha photons around to do this. And you don't need, again, you don't need many Lyman alpha photons, but you need some. So you need some stars to produce these UV photons. And if you go to early enough, the spin temperature will actually not couple to the kinetic temperature of the gas, but it will couple to the CMB temperature. It will couple to the photons. And then this term becomes 0. So you'll see, if you go to redshift 20, you may see some regions where there's no signal because the spin temperature is close to the CMB temperature, and other regions where there has been star formation, where you'll see this in absorption because it will still be cold. The Xray sources haven't worked on this yet, but the spin temperature couples to the gas temperature. So this period before substantial reionization is sometimes called the cosmic dawn. So the conclusions, the epoch of reionization is a watershed period in the history of the universe where it changed from neutral to ionized, from something that looks more like the CMB in some sense to something that looks more like the universe that we see around us today. There's been excellent progress, mostly with the Hubble Space Telescope, on detecting galaxies from that period, but detecting the galaxies is not enough. We have to detect the intergalactic medium to really understand what happened. And we're hoping to do this with LOFAR, and we are now starting to collect data, and within, well, maybe within a year we'll have some initial result, and it will take another 2 or 3 years to get deep enough to actually, for example, do proper power spectra. So most of the data will be statistical, but hopefully we can also do some very coarse images. And then high-resolution images and data on a much earlier cosmic dawn period should be produced by the SKA. So I thought I should go back to where I started with, the H2 region. So, because this is what brought me in Morelia in the first place. So I thought this would be an appropriate H2 region to show, because it's known as the Heart Nebula. It has a heart shape. And it shows exactly the kind of structures that I worked on with Will and Jane and Enrique. And it's beautiful, and it's a heart, so I love it. Now, interestingly enough, though, just before I left, I saw this picture. So this is a LOFAR observation of a particular region in the sky. And lo and behold, here's the Heart Nebula. It's seen by LOFAR at about 150 megahertz. So actually, this LOFAR telescope is not just useful to study reionization. I can even go back to H2 regions and look at them with LOFAR. So I love LOFAR, is what the author of this particular picture wrote, and I add an H2 regions on all scales. Thank you.
Can you please comment about the physical nature of these X-ray sources that you expect to have at Redshift 15, please?
So the idea is that these X-rays would be generated either by supernova remnants from the first generations of stars, or by the growing, maybe not yet supermassive black holes. So we know that by Redshift 7, there is a supermassive black hole. It's one of the highest redshift quasars. So they must have come from somewhere. They must have grown during this period. So it's either, or it could be X-ray binaries, actually.
Yeah,
this is all
microquasars, for instance.
And microquasars,
okay.
yes.
Is the limit on the detection of H1 in Redshift for LOFAR basically determined by the frequency coverage or by the sensitivity?
Well, they go hand in hand. Could you specify a bit more?
Well, I mean, the redshift that you're able to detect depends on your bandwidth, right?
Yes.
And so as you go further and further back to lower and lower frequencies, your sensitivity also becomes an issue. And I'm just curious whether what the limit is. Is it?
Well, so the HBAs only go to about 110 megahertz. And that's because beyond that, but it's a combination. But beyond that, we have the FM band, so we can't observe there. But at those low frequencies, so most of the sensitivity is mostly set by the noise level, which is set by the galaxy.
Right.
And so that goes up with frequency. So the sensitivity I quoted is sort of in the middle, but definitely it's harder to detect something at the low frequency end than at the high frequency.
So right now, though, you're getting down to, or you think you'll be able to get down to Z of 7 or 8. Is that? Did I get that right?
No, about 11 and a half, which is 115.
Okay.
But the quality of the data at those frequencies will be less.
Yeah.
So we may, for example, be able to get an RMS there, but maybe not very good power spectra. That's true.
Related to this question, so you mentioned that you had a 0.2 sigma detection for images. Is that for the entire duration? I assume you will be repeating these observations throughout the lifetime so far. So is that for the entire duration of the mission?
This is for that order of magnitude 1,000 hours of integration. So this is our 1,000, 2,000 hours is what we're aiming for.
You went very quickly through this part in your talk. Would you say that what is the most important result that will come out of these cycle zero observations, apart from maybe the epoch of reionization? I mean, you mentioned about several models. Could you elaborate a little bit more about that?
So are you asking what other science will come out?
About reionization. Apart from the epoch, you mentioned the models that one could discriminate.
Well, so cycle zero is just the first season of observations. So we don't expect, this will give us something like 200 or 300 hours of observation. So that is not really enough to make any detection, probably. But there will be subsequent cycles. So over a period of 2 or 3 years, we will be collecting thousands of hours, so 1,000, 2,000 hours is what we aim for, maybe 3. So from that, we will get basically a handle on how reionization developed, so when it was about 50% over, when it was about 30% over, and on the typical size scales of H2 regions at different times. So those are the two main ones. Then we may hope to pick up one or two very large ionized regions, which could then be interesting to do follow-up observations, to look for the many galaxies or maybe the bright quasar that should be sitting there that creates such a large region. But this is all on time scale of several years.
So, Garrelt, I was curious about the assumptions that have gone into your estimate of spin temperature. it would seem to me that what you're going to see and how you might interpret it can depend a lot on what happens to the excitation temperature in different regions at that particular redshift. It looks, if I've understood what you said, I think your modeling currently is just assuming that the excitation temperature might be a function of redshift, but you're not accounting for changes at that redshift in, so we say, more ionized or more neutral regions, which should be quite large enough that they might have their own ideas about what kind of excitation temperature they should have.
Right. So if the region is ionized, there is no 21 centimeter emission because it comes from neutral hydrogen. Then the spin temperature, so you can work out how, whether the spin temperature couples to the kinetic temperature of the gas or not. And that coupling goes through what is known as the Wauthausen field effect. And when you work out the levels of UV radiation to do that, it turns out that for reasonable expectations for star formation in the universe, you already at a redshift of 20 or 18 have enough UV background to couple to the kinetic temperature. So for LOFAR, we are very much after that. So we can expect the spin temperature to couple to the kinetic temperature. So then the question is, what is the kinetic temperature? So the kinetic temperature, we don't know this actually. But again, if you assume reasonable levels of X-ray sources, you find that the kinetic temperature of the gas will be quite easily like something like 200, 300 Kelvin. And then you're very much above the CMB temperature. And then the signal actually becomes insensitive to what the actual value of the spin temperature is. Now, if the X-ray sources don't exist, there will be cold spots in the signal, and they will cause absorption. And the absorption, the emission, here it is. So the emission could be for this set of parameters, the maximum is something like 27 millikelvin. But if you go to absorption, it could be easily minus 200 or minus 300. So we will very quickly pick up this if there is still absorption. The expectation is that there won't be. If there will be, it will be quite interesting because then apparently those X-ray sources that are thought to be there are not there. Now, if you have this, it will be more difficult to interpret the fluctuations if you have strong fluctuations in the spin temperature around the CMB value. That's definitely true. That hasn't really been explored very well, mostly because it's thought to be more relevant for the SKA, which is still in the future.